welcome to Chemistry for Non-Majors, Online Chemistry for Nurses. My name is Michelle Peters and I will be your professor for the next 8 weeks. Today we will be getting started on our introduction to chemistry and some of the very basic early concepts to build the foundation of our chemistry knowledge that we'll be acquiring over the next 8 weeks. Before you get ready to view today's lecture, you'll need to compile a few things at your workspace so that you are prepared while you're watching the movie. Some things that you'll need. You'll need to have a copy of today's learning objectives, week 1, lecture 1, and you can have those in a file just on a window on your computer brought up. You don't have to print them off. The purpose for giving you all of my learning objectives is for you to study for quizzes and exams. Everything that's on the learning objectives is fair game for any question that I could ask you on a homework, a quiz, or an exam. So it's really to inform how you want to be studying when it comes time for those type of assessments. So that's what good the learning objectives will serve you. You'll need to print a copy of homework 2 for submitting as homework. The way that I will collect your homework is I will have you download a copy. You will write on your copy of the homework or on a separate piece of paper, depending on if you need more space. If you write big, that's no problem. You can use as many pages as you want. And then when you're finished with your homework, you will scan it and email it back to me. Or, I'm sorry, not email, you will upload it on whatever module is listed for this week 1, lecture 1, or for wherever it tells you to upload homework number 2, that's where you'll put it. If you feel comfortable using a word processing program to enter your answers for the homework, you certainly can do that. I have a feeling it would take a lot less time for you to write up a hand, scan it, and upload it than to use a word processor. At least that's been my experience, but you can do whatever you feel is most necessary for you. You'll need the periodic table that I sent you in the packet of materials earlier last month. This is the periodic table that I am going to be referring to, so this is the one I want you to be using. That's why I sent it out to you as a hard copy. It has some pretty small writing on that, so I didn't think that it would be fair to ask you to print that. So that's why I sent you out that periodic table. And you will also need for tonight's lecture a copy of what I call the yellow sheet. It is Appendix 1, General Chemistry Formulas. It's unit conversion information, and I, from now on, will always refer to it as the yellow sheet. Then we will also need a calculator for tonight's class. Now, I use something fancy, this graphics calculator that I've had since I was in the 8th grade. You don't need anything like that. Please don't spend a lot of money for this class. You will need the log function, and you will need your calculator to be able to take numbers to a certain power. So any kind of, the big calculators with the big buttons that you might use for your own accounting at home, balancing the checkbook, that's not going to cut it. So you'll have to go out and find a calculator that has exponents and log capabilities. You can get a calculator like this at Walmart or a comparable department store for less than $10. Please don't spend any money. And if you need help figuring out which kind of calculator to buy, just shoot me an email and we can talk about that. Okay. So now that you have all of your materials acquired, we will start today's class. Now, when I'm talking about this, and I always say at the end of the lecture, you guys will already be able to view all the things that I have put on Joule when I say at the end of the lecture. So what I will do when I am done taping tonight is put all of my Smartboard notes on Joule as well. So if there's anything that you cannot see, if there's anything that you cannot understand, I'm not really happy about how my handwriting comes out on the Smartboard. So if you have any questions, it looks a little bit funny on the board, but if you pull up the actual document, it's quite a bit more crisp. So if you have any questions about that, you won't be able to raise your hand and ask and stop me from continuing on with my mistakes, but you'll be able to download and print or view these notes, so that will give you a different point of view, I guess. Okay, we have a lot of material to cover in the next 8 weeks, so we're going to have to push through things at a pretty quick pace. However, we're not going to go into the kind of depth that I normally go into in a general chemistry course when you have 2 15-week semesters to cover all of this information. So don't panic, don't be worried. Everything will be, I would say, pretty easy to understand, and I feel like I do a pretty good job of explaining things, but if you have questions, I can always explain them in an email or at a later date in one of my video lectures. Okay, so let's get started. I can, on the smartboard, switch between my different Word documents. So I'm just bringing up here the learning objectives for today's class. We're going to start with section 1 of your text, and we're going to go through a very brief overview of the study of chemistry. And then we'll go on to physical and chemical change, and all of that should be pretty self-explanatory. One moment. As you can see, this is my first time using a smartboard. Your patience is appreciated. The pointer's not working. I'm so sorry about that. Please bear with me. Okay. Chemistry is referred to as the central science, and it's because all of the other sciences are built upon chemical principles. And a lot of times in those other sciences, whatever biology, human biology, especially courses that you've taken in the past, they maybe don't talk about chemistry in its explicit terms. That's sort of why they're forcing you into my class. Okay, so let's dissect the definition of chemistry. Chemistry is the study of matter and its properties, the changes it undergoes, and the energy associated with those changes. Okay, that's a lot to digest. Let's break it apart. Chemistry is the study of matter. Matter is defined as anything that has mass. Okay, so now we're going back to about something that you probably learned in science in about 5th grade, mass. Mass is different than how much something weighs. Mass is defined as the amount of matter an object has. So anything that has mass is something that you can feel and touch and see, the tangibles. Chemistry doesn't have anything to do with things that don't have mass, ideas, thoughts, reflections. That's psychology, physiology, psychology, metaphysics, that kind of thing, not chemistry, because it doesn't have mass. If it doesn't have mass, it's not matter, so we don't worry about it. There are plenty of things in the universe for us to be concerned with because a lot of things have mass. So that is what matter is. Matter is anything that has mass. And then we talk about the properties that this matter has. When we're talking about these properties, there are 2 different types of properties that we concern ourselves with in chemistry. There are physical properties and chemical properties. And in the next section, we'll talk about the difference between those 2 and how you can differentiate between them. The changes this matter undergoes. There are also 2 different types of changes, chemical and physical. And the energy associated with these changes. one of the most important parts of the study of chemistry, is the energy associated with these changes. Systems strive for states of lower energy. That's why chemical reactions take place. That's why our bodies go through chemical reactions. That's why we age, to strive for states of lower energy. We'll talk about that in the coming weeks and in the coming lectures in more depth. But that's basically the solution to the riddle of life. All systems strive for states of lower energy. Okay. Toolbar, switch sides. Okay. There we go. Okay, let's talk about the different types of properties. There are physical properties and there are chemical properties. And you might think that, well, physical properties, doesn't that sound like something that we should be worrying about in physics? Remember that chemistry is the central science. So a lot of the things that we're talking about at the molecular level are things that are talked about in different disciplines like physics and biology at the more macroscopic level. Okay, so physical properties are properties that can be observed without changing the substance. And when we talk about without changing, we mean changing it chemically. That's rather important. Okay, so physical properties, you can observe them by looking at a substance or by doing something to it that's not a chemical change. Okay, so some physical properties are mass, and we can test an object's mass by weighing it. We can measure something's volume without changing it in any way. We're just putting it up to a measuring stick, basically. Density is a physical property. Density is equal to an object's mass divided by its volume. Therefore, if you can measure something's mass, you can measure its volume, you know what its density is. Some other things that can be measured without changing anything chemically, something's hardness. Diamond is the hardest substance that we have on planet Earth, and you can test its hardness without changing anything. You can take your diamond running ring and you can scrape it on a piece of glass to make sure it's legit. You're not changing anything chemically, so by just observing this, it's a physical property. Noticing something's color by just looking at it is a physical property. This is important to note because there is a difference between looking at something's color, just saying that my soup coat is gray, versus watching something change color in the course of a reaction. We'll talk about that in a little bit. So this is color just observing. Another chemical property, another physical property is something's state of matter. This is probably the most important physical property. A state of matter is, in other words, a substance's physical state. There are 3 states of matter. There are solids, liquids, and gases. And you can observe what state of matter your substance is by just looking at it. My water in this water bottle is a liquid. I'm not doing anything to it chemically, so just by looking at it I can see that it's liquid. But I also know that my water bottle itself is a solid. Physical properties. about the chemical properties. I like to use different colors so that maybe that will help to stick out in your mind. Chemical properties are properties, we'll call it a substance rather than an object. Properties a substance exhibits while or after undergoing a chemical reaction. RXN is how I abbreviate reaction. So you can mark that down for future reference. Okay. One problem about these smart boards is you run out of room. Okay. Some examples of chemical properties include flammability. Flammability is the chemical word for does it burn. The reason why flammability is a chemical property and not a physical property is because when something burns, it's actually undergoing a chemical reaction. So, the chemical reaction is called combustion. We'll get to that later. Another example of a chemical property is corrosiveness. Corrosiveness is the chemical term for will it react with an acid? An example of something that is not corrosive is titanium. Titanium, as you know, is a common metal used in hip or joint replacements. The reason why titanium is used in joint replacements is because it has a very low density, which means it doesn't weigh a lot, which is not ideal for a joint, and it doesn't react with acids and body fluids. This is optimal because you don't want something that's in the body to react at all with any of the bodily tissues, because if something is corrosive, the acids would eat it away. What would be the point of having your hip replaced if it's eventually going to be worse than the hip you've got now? So that is what corrosiveness is, the ability to react with acids. Another chemical property is general reactivity. This statement, or lack thereof, is the key part of the reactivity chemical property. So a property that iron has is that it rusts. In other words, iron metal reacts with oxygen in the atmosphere to form iron oxide, which is rust. Gold, however, is a metal that does not react with oxygen. So gold jewelry does not tarnish, it doesn't rust, it doesn't fade or discolor, because it does not react with the oxygen in the air. This property of gold, so that it does not react with oxygen, is a chemical property, even though it doesn't react. So reactivity, the reactivity of iron with oxygen, is a chemical property, as well as gold's inactivity with oxygen in the atmosphere. So this is a common thing that you'll see on your homework. I'll ask a question, or I'll identify as a chemical or a physical property, and I'll say something like, hip joint does not react with bodily tissues. Is that chemical or physical? Well, it is a chemical property because you're talking about something's reactivity, regardless of whether it reacts or not. Okay. So now we've talked about matter. We talked about properties, let's talk a little bit about changes. Remember, there are also two types of changes, physical and chemical. Physical changes result in usually the change of a substance from one state of matter to another. For example, when ice melts, it's going from a solid to a liquid. It's a change of state, therefore that's a physical change. My little 3-year-old loves macaroni and cheese. We call it mackin'. And this afternoon for lunch I made him some mackin', and I had to boil water. Water is going from a liquid to a gas as it's, bubbles are coming up. The steam is released into the atmosphere, changing from liquid to gas. That's a change of state, a physical change, not chemical. Another type of physical change is anything that changes the appearance of your substance without changing it chemically. So something like bending a strip of metal, smashing something, pulverizing something, your arm gets broken, physical change. The whole healing process of your arm getting broken is chemical. We'll talk about that. Okay, so in order for you to have a chemical reaction, you have to change the chemical composition of your substance. The only real way you can know if your chemical composition has changed is if you can see the little atoms and see that they're somehow different. Well, obviously we don't have atom vision, so you have to look for obvious, noticeable, visual signs of that a chemical reaction is taking place. We're looking for visual evidence. Some of that visual evidence includes a color change. If while heating something you're changing from one color to another, that substance has undergone a chemical change. A smell change, I guess. It's an awkward way of putting it, but if all of a sudden an aroma is produced, let's think about burning toast or burning popcorn. Not very pleasant, and your toast didn't smell like that before. So when you have a change in smell, or a new odor, usually it's bad, is produced, that means you have a chemical change. Another visual sign is that a gas is produced. Now, this is something that can be very tricky because gas is sometimes produced with a physical change as well. This is something that we would spend more time talking about in a regular general chemistry class because we'd have more time, or we would have a lab to investigate this. So, for now, we won't worry too much about that. Okay. So if you look back to your learning objectives, you can look back in well, I thought it would let me write. Anyways, you can look back on your learning objectives, and here is where you could stop your lecture, stop your video, and you could take the time to fill in these definitions, answer these questions, elaborate on this outline that I have here after listening to me talk. Going back and comparing these objectives with what you see on your smartboard notes. Or you can do this at a later date, you know, when you're studying the night before the test too. It's totally up to you. Okay, so we've got all of section 1 covered so far. Oh, let's practice a little bit of distinguishing between chemical and physical change. So if you take a look at your homework 2, oh brother. Okay. So on page 2, you have to identify all of these cases as either a physical or chemical change or property. Okay, so let's just take a look at the first 5. A plum ripens. Okay, so you could observe a plum ripening, getting bigger, changing color. If something changes color, that's a chemical change. Water boiling on the stove, we just talked about that in reference to the making of the mackin. That's a physical change because you're changing only from liquid to gas. When you're talking about a plum ripening, that has to undergo your plum has to undergo a series of chemical reactions for it to ripen. A glass window breaks. Are you changing chemical composition? Is there a smell? Color change? That's a physical property. An inflated balloon gets larger when heated. Okay, so you're inflating something and it's getting bigger because you're heating it. Your volume is increasing, but you're not changing anything chemically. You're not adding a different gas to the inside of the balloon. It's a physical change. And number 5, a silver tray tarnishes. Well, we just were talking about how gold doesn't tarnish in the presence of oxygen. Silver does not have that. So you'll notice that your silver jewelry, if you don't wear it for a time, or silverware, you have to polish that every once and again. It's because silver reacts with oxygen. That is a chemical change. The best way to differentiate between these two, chemical and physical change, is to ask yourself, can you undo it? Can you unburn toast? No. If your answer is no, you most likely have a chemical reaction. If your answer is yes, you most likely have a physical reaction. This isn't infallible, but it's a good thing to think about. If you cut your hair, can you uncut your hair? Well, not really. You're not going to really tape your hair back on, but it will grow back, so that the mere cutting of it is just a physical change. If you bake cookies, if you turn your cookie dough into, a real cookie, can you undo that? No, you can't make it that delicious dough again. So that's a chemical change. This is usually the point where I ask if there are any questions. And if you have any questions about any of these lecture topics, please feel free to either email me or post them in a forum discussion so that the others can see what your questions are. And if you have any questions that you want me to address personally, as long as you send them to me before my next taping session, I would be happy to answer them for you on the email. Okay. Let's move on to some math stuff. So we have to spend some time talking about what's called significant figures. Some of you may be familiar with this term, this topic, and others of you may not be familiar with it at all. I will tell you up front that it is something that you will have to struggle with for the rest of the 8 weeks that we have together. After that, you probably won't use it unless you go into chemistry. We will spend very brief time on it, but in today's lecture, but I will have, you can go back and look at this lecture if you have confusion. And it's something that does cause a considerable amount of confusion for a lot of students. I have what I think is a pretty good way of explaining it to eliminate some of that confusion. However, it's just one of those things where you just have to muddle through. Okay, so we use significant figures to determine how precise we need to be with any of our measurements. It's the reason why sometimes you see 1.00 milliliters versus just 1 milliliter. The 2 zeros at the end increase the number of significant figures in our number. The purpose for this is to tell you how exact you need to be with your measuring. If you're only measuring 1 milliliter with only one significant number, it means that you don't have to be very precise with your measurement. On the other hand, if you have to measure 1.00, it means that you have to get this number to the next, to 2 decimal places. That means you have to use a higher degree of precision and accuracy, and you have to use a much more refined technique. Okay, so let's talk about how we determine significant figures. There are a whole list of rules, and just like for most of the topics that we'll be discussing, I've come up with for you a series of rules that if you follow these rules, you should probably never go wrong. Okay, the first rule in determining significant figures is that all non-zero numbers are significant. And a word you don't see a lot in chemistry, always. So anytime you have a number other than 0, that particular digit is always significant. So that would be 1 through 9. That's the really easy part. That's the only thing easy about significant figures. Okay. That leaves us with the lovely old 0 to talk about. 0 is what makes this so confusing. Okay. There are 3 different places that zeros can be in a number. At the beginning, in the middle, and at the end. There's a different rule for each of those placements. So, when a 0 occurs at the beginning of a number, it's really hard to spell when you're writing at the board. If I make spelling errors, I really apologize. Okay. If a 0 occurs at the beginning of the number, in other words, if 0 is the first number in your number, something like this, 0.10. If that 0 occurs at the beginning, it is not significant. The only time you usually see a 0 at the beginning of a number is when you have a number that's less than 1. In other words, 0, decimal point, some number. This brings me to my next discussion. You are all nurses, and if you are not in this habit already, you need to get into this habit right away. The habit is to always write the 0 in front of that decimal place. From now until we are done in 8 weeks, I will take off a half point on every single problem in your answer where you do not write that 0 in front of the decimal point. It's really that important. I don't have to spend too much time explaining this to you because you are all healthcare professionals and you understand the difference between a medication that's prescribed at 0.1 grams versus 1 grams. You all have seen what doctors' handwriting look like. My dad is a pharmacist, and I've seen what pharmacists' handwriting looks like. It's bad, very bad. That dot can really get lost. But if there's a 0 in front of it, you always know that there's that decimal point there. Nobody writes a 0 in front of a number if there's no decimal point there. So that's not an issue. The reason we write the 0 is to differentiate between a whole factor of 10 that can be a matter of life and death for your patients. So please, please, if you're not in the habit already, get in this habit because you will be penalized if you do Okay, so that was my diatribe on the zero. That is a question on your learning check at the end of this lecture, so make sure you took good notes on that. Okay, so back to our rules here. If you have a zero at the beginning of a number, it is not significant. Now, what happens if you have a number that's a lot less than 1, and there are a whole bunch of zeros? All of these zeros still are at the beginning of the number. There's no other non-zero yet until you get all the way over here. Therefore, none of these zeros are significant. They're merely placeholders to tell you that this number is 1,000 times, or 3 powers of magnitude, I guess, less than 1. Okay, so zeros at the beginning are not ever, 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 ever significant. Okay, if a zero is in the middle of a number, and in other words, there are 2 non-zeros around it, if that zero is in the middle, it is always significant. What does that look like? Here you have 2 different numbers where your zero is in between 2 non-zeros. This zero is significant. Both of these zeros are significant. If it is in between 2 non-zeros, it is significant. Okay, both parts A and B were pretty easy compared to part C. This is the part that's the trickiest for most students. If you have a zero at the end of a number, there are 2 caveats. Here's what they are. So, if your zero is at the end of your number, and if there is a decimal point, decimal point is the dot in the number. If there is a decimal point, those zeros at the end are significant. The key to case 1 is that it doesn't matter where the decimal point is in your number. As long as there is one, all of the zeros at the end of your number are significant. Okay, what does this look like? Here are some examples. Here your number ends with these 2 zeros. These zeros are at the end. If there is a decimal point, it doesn't matter where the decimal point is. There it is. That means those zeros are significant. So if you were asked to identify how many total significant figures are in this number, there would be 4. I abbreviated that SF. There are 4 significant figures. How many significant figures are in this number? Well, the ones and the 2's, those are easy because we know those are always significant. And here we have a 0 at the very end of the number. These zeros now are in the middle. Those numbers are always significant. So far we have 1, 2, 3, 4, 5. This 0 is significant because there's a decimal point here. So there are a total of 6 significant figures here in this number. Here's a tricky one. Here you have the case where you have zeros at the beginning of a number and at the end of the number. Remember from our previous discussion that zeros at the beginning of a number are not significant. That number 1 is always significant. And now here these 2 zeros are significant because they're at the end and there's a decimal place. So how many total significant figures? 4. 3. Okay. Oops. Oops. This is confusing here. Sorry about that. If there is no decimal point, they are not significant. Okay, what does that look like? Well, let's say we have 1200. Those zeros are at the end, but there's no decimal point anywhere in that number. Therefore, those zeros are not significant. There are a total of 2 sig figs in this number. Here we have an interesting case. We have a 0 in the middle, always significant, and 1 at the end. This is a comma because I have 12,010 here, this number. There's no decimal point, so that means that this number 0 here is not significant. There's a total of 4 sig figs. And now for the really tricky question. What if you have something really weird like this, where you have the decimal point right at the end, there aren't any numbers after that decimal point, but you've got 2 zeros hanging out here? Remember I said it doesn't matter at all where that decimal point is, it just has to be in the number? In this case, there's a decimal point, they are significant, so that means in this number, there are 4 sig figs. I know this is tricky and I just did a lot of talking. So let's do a couple of examples to help you practice some of these concepts. For the time being, it's okay to have your notes out here. Oh, shoot. I forgot that I don't have to erase. This is really hard for me to get used to. I'll go back and fix that before I upload that. There we go. Sorry about that. Okay, here are a bunch of examples. I am going to write them all on the board, and then I want you to pause it and write your own answers in. Take a moment, pause the video, and write down your answers. I just want the note to know how many significant figures are in each of these numbers. Okay, let's talk about each one of these. Here you have a decimal point, your zero's at the end, that means that 0 is significant. You have 3 sig figs. No decimal point, not significant. A decimal point, significant. A decimal point here, but these zeros are in the middle, and remember that 0 at the beginning is not ever significant. 4 total. 3, not, yes, decimal point. No decimal point, not significant. No zeros, easy. 1 one significant figure. No decimal point, not significant. No decimal point, not significant. Decimal point, significant. That's 5. At the beginning, not significant. In the middle, significant. At the end, decimal point, good. 1, 2, 3, 4, 5, 6. No zeros. Yes. At the end, decimal. No zeros. In the middle, at the end, beginning. No, yes, yes. Decimal point, yes, yes. Yes. Now, if you take a look at your homework, oh, dang it. Well, either way, there's a section in your homework where it asks you to circle what zeros are significant. If you have a question like on page 1, number 3, take a look at number 3 on your homework. You'll notice that you have 300. There are no decimal place, there is no decimal point, and those zeros are at the end. That means those zeros are not significant. So you don't have any significant zeros in number 3. What I'd like you to do right there on that one is write none. That'll help me to know that you didn't just skip that problem over and you got lucky, but that you identify that there are no significant zeros. And that's all there is to know about significant figures. If you are confused at all, or if you're having a hard time identifying these examples, excuse me, go back, review the lecture, take a look at the Smartboard notes about each of the different cases of where that zero can be, and try to discern if you can find out where you're going wrong, where your mistake is. If you're still having problems at that point, shoot me an email and maybe we can talk about a different way of explaining how to figure out if those zeros are significant or not. Okay. If you are having a hard time, take a break for now and come back later. We are going to be moving on to scientific notation. Scientific notation is a great way of writing numbers to eliminate the confusion of whether or not a number is significant in an answer. And basically all we're doing in scientific notation is moving the decimal point and multiplying by a factor of 10 to make things more clear. The best time to use scientific notation is when you have either a really small or a really large number. Okay, so what we're going to be doing here with this scientific notation is we're going to be taking this decimal point and shifting it either to the left or to the right to change how the number is written. Now, in scientific notation, the whole point is to have only one number to the left of the decimal point. And that number cannot be 0. Okay, so the first thing that you're going to do in writing a number in scientific notation is to identify where your first non-zero number is. In our really small number, that first non-zero is right here. So we're going to take our decimal point place and move it so that this number is the only number that's to the left of the decimal. So that means we're going to have to move it 1, 2, 3 times. Keep that number 3 in your mind. So now that we've moved the decimal point there, I'm going to rewrite that number as 1.02. Because we've moved the decimal point, all of these zeros are useless. We don't write this, so you can just drop them. Oh, brother. Okay. Now, remember that we had to move that decimal place 3 times? Well, we have to account for that somewhere in this number, because this number is not the same number as 1.02. So what we're going to have to do is multiply 1.02 by a factor of 10. Now, we moved the decimal place 3 times, so we have to move it by 10 to the power of 3. And because we had to move the decimal place to the right, and because this is a really small number, we have to identify that as a negative 3. The negative exponent is for numbers less than 1. The positive number exponent is for numbers greater than 1. In other words,